I'll share. Okay, can you see it?
Yes, yes.
Okay. Perfect.
Welcome everyone for our resumption of quantum space-time seminar series. I hope you guys are not very tired after the 2 weeks of strings. Today we are very happy to have Raghu Mahajan from Stanford University, and he's going to tell us about, okay, I don't know what the title of the
Yes,
talk.
it's a sphere partition functions in string theory.
Go ahead.
Okay, so this talk will be based on a paper that just appeared a few hours ago with Douglas Stanford and Cynthia Yan, who's a young graduate student at Stanford. And so the basic point of our computation is we want to compute the sphere partition function, but without any vertex operator insertions. So usually if we open Polchinski's textbook, you start with the 3-point function of tachyons. So that's some scattering amplitude, 2-to-1 scattering amplitude of tachyon. But you can ask, what is the sphere with 2 or 1 or 0 vertex operator insertions? In particular, the object with 0 vertex operators, there is an expectation that that sphere diagram should give the classical value of the on-shell action of the background in which the string is propagating. So this is important because we want to know the on-shell actions in things related to black hole thermodynamics, or in ADS-CFT, the on-shell action of ADS3, for example, or any ADS space encodes its thermodynamics. So we want to study things like Bekenstein-Hawking entropy, the Gibbons-Hawking, formalism within the context of the string worldsheet, and how does the string worldsheet know about the Gibbons-Hawking term, for example. So these are the kind of questions. And a preliminary comment is that all of these quantities, like the Bekenstein-Hawking entropy, are proportional to 1 over G Newton, which is 1 over G string squared, which is the genus counting of the sphere diagram. So that's the power counting. But anyway, the puzzle in computing the
Sorry, sorry, Raghu. Now, I really shouldn't interrupt so early, but since you had those comments at the end of the first slide, I can ask you, you can come back to it wherever, which is one reason why we believe the sphere partition function vanishes, at least for only NSNS backgrounds, is what you said, that there's a 1 over G string square out in front of the action, and then isn't it that the dilaton equation of motion would give us that the on-shell action would vanish?
The bulk contribution is 0.
Okay.
I have it on this thing, but there could be boundary contributions.
Okay, I see.
Yeah.
All right, please.
Right. So one of the puzzles is that the sphere without any vertex operator insertions has a PSL2C conformal symmetry, which we have to divide by in the path integral. And PSL2C is non-compact, its volume is infinite. So you might think that the answer is 0. But point is, there's also an infinity in the numerator. The target space that strings move in is usually non-compact, like Minkowski space or ADS space. So it's really ill-defined. There's an infinity in the numerator from the non-compactness of the target space. So the string can be located anywhere in the space-time. And there is an infinity from the PSL2C in the denominator. Okay, so this is actually unlike the case of the disk, where there's a paper by Liu and Polchinski where the analog gauge group PSL2R has a finite regularized value. You just put some cutoff on the group, and there's a power law divergence, but you have a finite piece. That's not very satisfactory to replace the volume of a non-compact gauge group by a finite value, but one can do the supersymmetric version of that. And the volume of the supergroup is actually finite. The volume of OSP1.
Sorry, Raghu, can I? So the volume of the PSL2C is also in the numerator, isn't it? I mean, that's an infinity, not 1 over infinity. I mean, that is why you have to divide by it.
Well, it is there in the numerator somehow, but we don't explicitly have it, right? So there are some fields that are, usually we have like integral d phi and so on.
Yeah, but no, I just meant the numerator versus, I mean, it's actually an infinity, it's not a 0. The PSL2C is an infinity. You have to get rid of it. You have to, I mean, it's like in standard gauge theory.
Yeah. Yes,
Yeah.
that's part of the point, but the explicit thing that appears, so one would expect from what Gautam is saying, one would expect that one should get a finite value for the sphere partition function, right? Because you're saying that this thing should cancel, like in any gauge theory, partition function should have some value. But anyway, let's move on. These are just some preliminary comments. It will become clear. But anyway, the point I wanted to make about the disk is that if you put this finite volume of the OSP group, you get the correct D-brane tension. So you can use this to give a first principles derivation from the path integral of the tension of a D-brane. Just doing some bosonic path integrals, like free Gaussian path integrals on the disk. Okay, so what seems reasonably clear now, I'm on this page 3, the top part, is as Sandeep anticipated, that the sphere diagram is 0 up to effects having to do with the non-compactness of the target space. And as Sandeep was also mentioning and emphasized in these papers by Seitlin, that the bulk part of the action is just 0. It's enforced by the dilaton equations of motion, but there could be boundary terms. And I would like to remind you that even in the Gibbons-Hawking procedure, most of the action comes from the boundary terms, like the Gibbons-Hawking boundary term and the counter terms and so on. So the status is not really clear. And basically we suspect. Yes,
Raghu,
sure.
If we were looking at a black hole background,
Yes.
would you expect to get contributions both from the horizon and the boundary, or just the boundary?
But if we just look at the Schwarzschild black hole in flat space, the on-shell action is just the Ricci scalar, which is 0 on the Euclidean disk. But
up to possible boundary terms.
Yeah, the horizon is not a real boundary in Euclidean space, so we don't get any terms from there.
You don't get any terms. Okay, thank you. Yes.
Yeah, and I should say there was one paper that also by, I think, Shiraz and Matt Hedrick referred to these papers by Seitlin quite a bit. And there's some puzzle, like I think this whole story with the bulk terms in string theory is a bit murky. But we suspect that the resolution of the sphere puzzle from the worldsheet perspective will involve somehow putting a radial cutoff on the space-time on the string worldsheet. So how do we regulate the non-compactness of target space on the string worldsheet? And we don't know how to do this. And this is an open problem.
Sorry, could you tell me that the space-time that you are in, that's asymptotically flat, or it's now you are working in ADS?
It could be. These are general comments, so they apply to both.
No, because in ADS3, the dilaton is a constant. And you are saying that that equations of motion of the dilaton is going to, once you impose, you get this conclusion, but in ADS3, the dilaton is a constant, right?
Dilaton is a constant on shell, you mean? But
I mean, the supergravity dilaton in ADS3 with the pure NSNS flux, it's a constant. It's
well, the equation that you're talking about is the equation of motion. So it could have some on-shell value, some constant, but there's an equation of motion that you plug into the action, and you explicitly see that it's just a boundary term.
No, but then what is the supergravity background then in that case? Because if I just write you the supergravity background of the ADS3 in the pure NSNS part, you have the metric, the B field, and the dilaton, which is a constant. So I just want to know what is the supergravity background you are working, where you.
Well, I'm not in the most of the talk. I'm not going to work in any supergravity background. I'm going to work in the non-critical string theory.
Okay.
Anyway, so basically there is a happy place where one can actually compute all these the sphere and the disk very explicitly, and that is non-critical string theory. So you take Liouville CFT, coupled with a 2, P minimal model. And we would like to study it in the semi-classical limit of C Liouville going to plus infinity, which means this P is very large and positive. And so you have the 2, P minimal model, its central charge is going to minus infinity. And the Liouville plus the 2, P plus the BC central charge is 0 as we want. So this computation was actually done in a paper by Zamolodchikov from like 1982. but it was a bit sketchy and he didn't work out the order one constant. So we will compute the one loop determinants. And the whole pain in this paper was to get the precise numerical value correct. What do I mean by precise numerical value? The fact is you can compare it to the matrix integral computation. There's a dual matrix integral for each of these theories as a function of P. So you get a number on one side, you get a number on the other side, and you can match it. And yeah, it indeed agrees between the two things. Anyway, one comment is that one could get exact in B formulas for the sphere partition function in Liouville by taking the DOZZ formula when all the operators are like e to the 2b phi, where b is the cosmological constant operator, e to the 2b phi, because the 3-point function of that operator is the third derivative of z with respect to mu. So if you know the third derivative of z with respect to mu, you can just integrate it 3 times. Mu is the cosmological constant of Liouville. But we will not use this approach because we are interested in some conceptual points, and we will do a direct semi-classical path integral computation of the Liouville path integral. So that corresponds to this central charge of Liouville going to plus infinity. So basically, there will be some saddle points in one loop determinants and so on. And here is the main punchline of the talk, which I would like to emphasize, is that if we look at sphere worldsheets, the Liouville field has a saddle point. It's just, if you work with a sphere background metric, it's just some constant. But the point is, this saddle point breaks the PSL2C conformal symmetry. That means when you act on it with the PSL2C, you generate new configurations of the Liouville field. So actually, there is a non-compact family of saddle points, which you have to sum over. So that gives you some infinite contribution in the numerator. And because those configurations are being generated by the action of PSL2C, the non-compactness of PSL2C exactly cancels in the ratio. So this is exactly like Gautam was saying, but this is how it works in this example.
Sorry, yes. Raghu, please go on. Now I'm a little confused, so I just want to ask you, and then you answer when you like.
Yeah.
I mean, these I know nothing about 2,p minimal models, but these non-compact Goldstone bosons arise from there or where? I didn't understand.
They arise from just the Liouville action.
Oh, so that has non-compact directions then, is it? Just in the Liouville field?
Yeah, so the Liouville field is a non-compact field. Okay. It's a scalar field which takes values in R.
I see.
So on the sphere, you decompose it into spherical harmonics.
Got it. Okay, so don't you have zero mode? Then are you saying there's a zero mode basically because you're breaking?
Yes, there is a zero mode. Yes, there are 3 zero modes.
3 zero modes, yeah.
Corresponding to the L equal to 1 sector of the spherical harmonic.
Now I understand. So it's just that yes, you will have 3 zero. If you're going to break SL2C, you're going to get 3 zero modes from the Liouville. And
there are 3 that are not zero modes because a part of PSL2C is PSU2, which are isometries of the sphere. So the SU2 subgroup of PSL2C is sterile. It doesn't act on the saddle point.
I see.
And so there are 3 generators that generate this non-compact manifold of saddle points.
I see. Okay, beautiful. Thank you.
Sorry, Raghu.
Yes.
If I understood right, it was important that your solution, your saddle point solution, broke your.
Yes.
Now,
PSL2C. Yes.
Right. Now, if we take a saddle point solution, so I suppose the saddle point solution for just string theory in flat space would be x equals 0, right?
Yeah.
Now that does not break any symmetry. So would this philosophy work also for that situation? No.
That's why I said it's possibly irrelevant to the critical string, but anyway, it's yeah.
Thank you.
Right. So of course, now there are further subtleties because we want to match a precise number. You know, if we recall the old literature on Liouville, the sphere partition functions are always mu to the some power, mu to the some fractional power. And that it's easy to get that power right. But we are interested in the coefficient. But to talk about the coefficient, we have to say what we mean by mu. mu is basically a dimensionful parameter. So you have to compute some dimensionless ratio. And basically we compute this ratio sphere over disk squared, because the exponent of mu that appears in the disk is half of the sphere. So the sphere goes like G string to the -2, disk goes like G string to the -1. So when you take this ratio, all ambiguity in what we mean by the string coupling constant, which is the Liouville cosmological constant in this case, they go away. And this is the number that we would be able to match to the matrix integral predictions. So this is what we will compute. It's not just the sphere, but you need some reference point to talk about the sphere, like what is the number you're computing. Anyway, the final answer as a function of p is given here, is log z. There is just some e to the s naught is mu, and there's just some function of p that appears. So the point is the final answer is not the point here. The point is the conceptual way we arrive at the answer. And one point I would like to note is in the large p limit, this system goes over to JT gravity, and you see that the answer is divergent in the JT limit. So that's just a side comment.
But since you make it, and again, feel free to just come back whenever you want, is the statement that, in JT gravity on the sphere, I mean, can you say something? You do expect these saddle points, but there's a sort of the infinity upstairs is bigger in some sense, or what's
I think the point is that in JT gravity you get an infinity because let's look at this formula for the density of states at general p.
Mm-hmm.
So it's a sinh of p arc cosh. So this is some polynomial, but the point is there is this 8 pi squared over p squared here.
Mm-hmm.
And why it's there is to cancel this p outside.
Mm-hmm.
Because you want the p goes to infinity limit to be smooth, to be able to talk about JT gravity.
Mm-hmm.
And because you have this 8 pi squared over p squared to talk about the square root edge. So basically when p goes to infinity, this would just become sinh of square root of e.
Mm-hmm.
That arc cosh will simplify. So this is the sinh of square root of e. But because you have these powers of p here, this high power of p shows up in the numerator. So that's just the point, that
density
because
states in a sense. Okay.
Yeah, so it's like it's infinite relative to the density of states. It's not a finite. Yeah. So this ratio sphere over disk squared is divergent.
I see. And sorry, you must go on, but just to make sure, because at least as far as I could tell, the disk partition function certainly for JT is finite.
Yes.
There's some issues about regulating, but let's say it's finite. And
it is.
Yeah, and you would agree with that, right? So it's really the sphere which is divergent.
Yes.
Okay.
Yes.
Thank you.
Sorry, I missed that last exchange. Was there a physical consequence to the fact that the sphere partition function is divergent?
No, I don't think it has very much physical. Well, it's just because you see in JT gravity, the path integral wants to localize on configurations with r equals -2. So you naively think that there is no sphere configuration which has r equals -2. So you might say the answer is 0 or something, but the point is you have to compute it using this the p acts as a regulator in the computation. And when you just go ahead and do the computation, you find this.
There's no boundary. Is there a boundary dual to the sphere partition function of JT? Assuming that JT is sort of the low energy limit of SYK, the disk partition function is one insertion of the field theory. The sphere partition function sounds like no insertions of the field theory. So is there a boundary interpretation of this quantity?
Yes, it's just the computing the matrix integral, just computing the number, the L square term in the matrix integral. So just compute the integral and ask what's the log of the partition function and the leading term in the large L limit in that.
The matrix integral meaning the Sad-Shankar Stanford.
Or there is one for each p. There is a matrix integral for each p.
This is the matrix of the matrix that governs the eigenvalues of the Hamilton, the boundary Hamiltonian.
Yes.
Okay, good. So wait, so now I'm getting confused. If on one side you get infinity, and on the other side you get something finite. Sorry, why is this not? If you're saying that there's a boundary interpretation, why is it okay that you get infinity?
Well, it's because I think some of these things will become clear as we go on. So maybe
Okay.
let me
Thank you.
come back to
Yeah,
to the.
I just had a quick related question. So if I understood correct, what you're saying is that the matrix integral is the one that shows this p to the 5 thing that you wrote divided by p squared. That's the matrix integral answer, right? And that's the one that in the large p limit diverges. So
Yes,
I think
but they will agree. One of the points also.
Yeah.
Sorry,
So the matrix integral is what you've shown here, and that's the one that diverges. My question was, I thought you said the sphere partition function that you compute from the worldsheet side, from the bulk side, that because of this cancellation of the Liouville modes, that was essentially finite. So I'm
right.
trying.
So this is finite as a function of p, right? So for any fixed p, this is a finite number. So that was my first point.
On the other side also, you can see the same thing that.
Yes.
Because isn't
this formula, this p to the 5th over p squared minus 4, will be reproduced by independent computations from the Liouville and from the sphere and from the matrix.
I see. So you'll get exactly the same thing.
Yes.
Not just for the ratio of the sphere to the square, just directly for the sphere.
Yeah, maybe let me just present some more formulas, and then it will become clear what exactly we are computing.
Yeah.
Maybe this point about JT gravity was too early, like I shouldn't have put this in the beginning. Let's think of just the finite p theory. Sorry?
What is this symbol log z is what equal to what is
this? This will also become clear as we go on. So let me just say, let's forget about the JT thing. The point is there are string theories for each p. And for each p, this is the finite unambiguous answer for the sphere, which includes this cancellation that I was talking about.
Though, sorry, just one last sentence. Though the comparison that you're making, I mean, this was a semi-classical one in the Liouville. So in some sense, you can make the comparison not for each p, if I understood correctly, right?
Yeah, so in the semi-classical, p is large. So, well, you still have a function's worth of, you still match some function of p.
Okay, so
one could replace this by p cubed.
Leading p behavior you can match.
Yeah, exactly.
The p cube behavior, but not maybe the p squared minus 4.
Yeah.
Okay.
Okay, so basically, for most of the talk, I'm going to be talking about the Liouville path integral on the sphere, and the disk. Well, I'll talk about the disk lesser because it's better behaved with FZZT boundary conditions, and we'll stick to the semi-classical limit. So there are 3 components to any semi-classical computations in a gauge theory. You have to identify the relevant saddles, compute the one loop determinant, and divide by the volume of the gauge group. As already discussed, in the one loop determinant, the quadratic fluctuations, there are 0 modes. And these 0 modes are there because the saddle points break the PSL2C symmetry. So here is some more detail about what is broken and what is preserved. Out of PSL2C, SU2 is preserved because that's the isometric group of the sphere. And on the disk, out of PSL2R, a U1 will be preserved. That's just the rotation about the center of the disk. And to deal with things like the conformal anomaly and stuff like that, by disk, we will just use the reference metric, the hemisphere. So we will not work with the flat disk. We will work with half of the sphere with the boundary at the equator. Okay, so let's go on. So this is what we have to compute: sphere over PSL2C, disk over PSL2R. And as I said, emphasize that each of these has a dependence on the string coupling constant. So sphere is like G string to the -2, disk is G string to the -1. And we can't compare an absolute notion of G string in dual theory. So we have to compute something invariant. And this equation 1.1 is the invariant object. So the sphere divided by the disk squared. And it will also be important to know what measure we put on these groups, right? Because I mean, a priori, the Haar measure on a group has an arbitrary constant in front. But the point is that in string theory, these gauge groups arrive from the C goes to 0 modes. So really, to compare the PSL2C and the PSL2R, we should just look at the norms of the C goes to 0 modes. And that fixes the relative normalization of the Haar measure on PSL2C and the Haar measure on PSL2R. And that's important to get if you worry about getting all the factors of 2 and so on correct. So here is just the setup. The hats denote the reference metric. Sigma is the Liouville field. So the physical metric is in equation 1.2. The background will be a sphere or a hemisphere. And the background K hat on the equator is 0 because that's a geodesic. So here's B. The central charge of Liouville is given by this formula 1 + 6, 1 over B plus B whole squared. And we'll be taking B small. And here is the Liouville action. It's proportional to 1 over B squared. So the action is large in the small b limit, which is what gives us the semiclassical limit. Okay, so there's a boundary cosmological constant, there's a cosmological constant, there's a linear dilaton term. And it's important to keep these order 1 terms in equation 1.4. They come from the fact that the Q in Liouville is 1 over B plus B. So if we pull out a B, it's 1 over B squared plus 1. So these are sort of the pieces that are left over from the Q, from the +1 piece in the Q. Anyway, so now we get to the meat of it. So what are the saddle points? So on the sphere, you just find a saddle point, which is a constant. You vary this action. Don't worry about the kinetic term. Set r hat to 2, and it's just 1 + 4 pi mu e to the 2 sigma equals 0. Now, note that this means that e to the 2 sigma is negative. So it has an odd pi multiple of imaginary part. Now, this is how Liouville theory manages to have a saddle point for the sphere. It's like a metric with a minus signature, right? E to the 2 sigma is negative. Notice that the physical metric had an e to the 2 sigma in it. But it's fine. Path integrals are integrals, and if the defining contour can be deformed to pass through a complex valued saddle point, it's valid to include it. So just to emphasize this point one more time, classical Liouville theory is a theory of constant negative curvature metrics. And here, a metric, the sphere metric with signature minus has Ricci scalar -2. So we see that there is this infinite family of saddle points, which are just constants, but differ by their imaginary parts. And there was a related discussion of this in a paper by Maldacena, Yang, and Turiachi on de Sitter JT gravity. And okay, so we can take these saddle points, plug them into the action. The action will have some oscillating piece coming from the imaginary part of sigma. And now, okay, but there's some mu and so on anyway. So there is some on-shell action. Oh, which of these saddle points are we supposed to sum over? It's actually an important question to get this right. And the answer was contained in a paper of Harlow, Maltz, and Witten, which was talking about analytic continuation of Liouville theory. And as I will show you on the next page, the correct answer is to sum over the solutions is basically half of them with n equals 0, 1, 2, etc. So what happens when you do this sum is that this phase factor is a geometric series, and a geometric series with some complex ratio, and that gives you this sign in the denominator in 1.7. So it's important because if one looks at Liouville formulas, there are all these 1 over sine pi over b squareds, and that is where they come from. And importantly, it gives you this factor of 2 here. Okay,
so is this roughly because your original integration contour is a real contour, and then you want to just pick up poles on the, not poles, you want to deform this thing on this, let's say, arc on one side, so you only pick up the positive.
Yeah, so this is the figure here in 1.9. So
okay. Yeah, okay, fine.
So yeah, so if the defining contour is actually not completely along the real axis, because the zero mode integral of phi looks like equation 1.8. So when sigma is large and positive, this exponential is convergent. This a sigma doesn't matter. You have a huge exponential suppression coming from this e to the 2 sigma. But when sigma is large and negative, this e to the 2 sigma is not important. And then the convergence property is determined by the sign of a. And if you look at the Liouville problem, a is actually negative. So this integral, you actually don't define it on the real axis. You can define it, but there will be some ambiguities in it. Like it's strictly speaking not well defined. And this is a well-known problem in this minimal string literature. All the partition functions that you compute have ambiguities that are analytic in mu. So this contour ambiguity reflects the fact that the sphere partition function in Liouville can have integer powers of mu, and those cannot be reliably computed. Those are not universal and are not computed by the matrix. So that is why I had this containment sign in the log z, because you don't compute terms that are integer powers of mu. They are non-universal, and if you think about triangulating the surface and taking the continuum limit, they are not universal. So
sorry,
yes.
Sorry, again, you
Yes.
might well cover this, but will you explain a little more the Witten, Harlow, whatever reasoning? I mean, what is the, oh, I see. The
This is
defining
the
contour
reasoning.
is going up. Aha.
Yeah. So, and
choose-
what are the shown in dashed lines are, so the thick dots are the saddle points for all n.
Mhm.
And these dashed lines are the steepest descent contours. So you see that the defining contour, which is starting up and coming down and along the real axis, if you wrap it around n equal to 0, then n equals 1, then n equals 2, and n equals 3, and so. So this is basically the argument.
And the rationale for choosing this is simply that will give a well-defined path integral, or what? I mean, of course, you could
Yeah,
also
one could think of this as going to complex values of b, so making b slightly complex.
Okay.
Having
And
some certain imaginary part. Yeah.
I see. And could you have chosen a kind of complex conjugate contour also?
Yes. Yeah. That.
Okay. So that might reflect in some overall normalization, I don't know, of your integral.
We didn't check all the things, but I believe it would go through. Yeah.
Okay. Thank you.
That would just be the, I mean, you did this geometric sum, you could have easily done the geometric sum with the negative ones, and that would have given you, I think, the same answer.
Answer. I was thinking maybe the I goes to minus I or something. Okay.
That's what the complex conjugate, because because it's e to the I theta and e to the minus I theta.
Exactly. That's what I thought.
Except I think that in the positive sum, n equal to 0 is included, but
but you need that technique, right? That's how you would.
In this figure, it seems that if you bend the contour, defining contour downwards, then you will miss the n equal to 0.
No, but
but the exponential was 1 plus 2n. The exponential was 1 plus 2n. So the exponentials you're summing are 1 plus 3 plus 5 plus 7.
True.
And in the other side, you would be summing minus 1, minus 3, minus 5, minus 7.
Okay, got it. Thank you.
Okay. And then you can play this. So the sphere is done. So far, we have figured out what the saddle points for the sphere are and what their steepest descent contours are, and which of those we are supposed to sum over. You can do the same thing for the disk. So you take the hemisphere. Now sigma is no longer constant. You have to take at least sigma to be a function of theta, the polar coordinate on the sphere. You get some differential equation, you get some boundary condition. The thing I would like to highlight is boundary condition contains this boundary cosmological constant. And again, you only determine e to the sigma. So there's again some family of saddle points that have some imaginary shifts in sigma. And okay, so I would like to now introduce this parameter alpha through this equation, which basically is just a function of mu b. And since the only purpose of the disk in this computation was to serve as a reference point for the sphere, we will just work in the limit of mu b large and negative which is alpha small and positive. And that's the limit in which we would compute the one loop determinant of the disk. Note that the metric, the Liouville field is non-trivial. It has this 2 alpha cos theta and so on. Basically, if you take this and multiply with the metric of the hemisphere, you will see that it is just the hyperbolic disk. Because for the disk, the Liouville theory has a classical solution. It wants to be the negatively curved hyperbolic space. Here, we have just picked a funny reference metric, which was positively curved. So this funny e to the 2 sigma is compensating the positive curvature and giving you r equals -2 for the actual physical metric. So that is the condition here. Anyway, so then you can again compute the on-shell action, which I have displayed in this equation 1.14. There's some action. And as I said, it is simple to just work in the limit of small alpha. And then this 1.15 is the simplified form of the classical action. Now here we can already see that things will become nice in the ratio sphere over disk squared. Notice that the power of mu will cancel. So here mu has a square root and has this power 1 over b squared plus 1. And in the sphere, it had just mu to that same power. So this is what I mean by canceling the mu dependence, because there is no dual of mu in the matrix sign. There is no direct dual of mu in the matrix sign. A numerically precise dual. Anyway, so then again, we sum over these saddle points and so on and so forth. So now we are done with the part about the on-shell actions. Next comes the one loop determinants. This is straightforward, though again, it's a pain to get all the constants right. So we are supposed to look at fluctuations around the saddle point denoted by these field chi. You have to define a metric on field space. A d chi refers to a small change in chi. And this parentheses round brackets is the inner product on fields on the space that we are considering. So this d2x could be the sphere or the hemisphere. But the point is we have to use the same capital C for all manifolds in the theory, for the sphere, hemisphere, and so on. So this is really the definition of the path integral on all two-dimensional surfaces. So now let's see. So now let's look at the sphere. What is the quadratic action? Quadratic action is very simple. It just looks like a scalar with a negative mass, -2. So what is going on? So first of all, notice that there is a negative mode. The chi equals constant has a negative eigenvalue. And that just corresponds to the fact that the steepest descent contour is vertical through all these saddle points. So there's some I that you pick up when you do the steepest descent integral. So that's the L equal to 0 eigenvalue. But the L equal to 1 eigenvalue is 0. It's L plus 1 minus 2. So those are the 3 zero modes that I promised, which will generate the infinity in the numerator to cancel the 3 non-compact directions of PSL2C. And for L bigger than or equal to 2, you just have to compute the product. So sorry, I already said this. The L equal to 0 is just a 0 mode integral. You have to do it along the imaginary axis. And that particular contour prescription gives you this -I. So we also worried about the signs, and it's important to also get these signs right. And yeah, so this is the 0 mode contribution. You just put a delta function. So you don't want to integrate over the 0 modes. You want to cancel them with the gauge. And
sorry, the L equal to 0 mode, which was the constant 0 mode, you should have been, so in that graph of the saddle points, what that corresponds to some moving the saddle point along some direction?
No. So this L equal to 0 mode is not a 0 mode. It's just L equal to 0, but it has a negative eigenvalue, like it is -2 eigenvalue.
It's not an L equal to 0 mode.
Oh, sorry. Yeah. Okay.
Yeah.
So the 0 mode is L equal to 1.
Yes.
Okay.
Because it has a tachyonic mass. So
yeah. Sorry. Okay, fine.
Yeah, I was just saying the negative eigenvalue basically, gives you this I here. And there is another way to see the I, which is that the contour of integration is vertical instead of horizontal through the saddle point. Okay, anyway, and then for the L bigger than or equal to 2 modes, you just get some infinite product, raised to 2L plus 1, the degeneracy, and you just have to regulate it. And we regulate it in the very naive way. You put in a suppression factor, epsilon squared, LL plus 1, look at the small L limit. And this is basically, I don't know, easy stuff if you're used to computing one loop determinants. Okay, so here is the one of the constants that might appear later, for example. So anyway, that's the one loop part of the sphere. The one loop part of the disk is similar. So here, the fluctuation has a bulk action. So it just looks like grad chi squared, but it has a boundary term, chi squared. So this is a quadratic action. So you think you might be just solving the Laplacian on the sphere, an eigenvalue problem for the Laplacian, but with these Robin kind of boundary conditions. It's not Dirichlet or Neumann. It's that the derivative has to equal chi at the equator. And this problem is then qualitatively similar to the sphere. It has one negative eigenvalue. It has 2 zero modes. The 2 zero modes are written here explicitly, e to the plus minus I phi tan theta over 2. And a note that you might think this is badly behaved at theta equal to pi, it blows up, but the hemisphere goes only up to theta equal to pi over 2. So this is perfectly fine. And it satisfies this boundary condition and so on. So again, the story is similar. There is one negative eigenvalue, 2 zero modes, and then some infinite number of positive modes, which you have to regulate. And there is some subtlety in how you regulate it. I can come back to that later, but maybe let me go on. But it's a pretty straightforward computation of, again, some number like this, 1.114. There are some divergent terms that diverge with epsilon, some logarithmic terms and so on. But this is the finite piece. Okay, so now we are done with the
Sorry, Raghu, just to understand. So the 2 zero modes are two generators of SL2R.
Yes.
And the U1 part of it, I think you said that
is an isometry.
Is an actual isometry. Okay.
Yeah. So the U1 doesn't even act on the saddle. So it doesn't generate new saddles.
New solutions. Okay. I fully understand. Yes. Yes. Okay.
Okay.
What do you do to the 1 over epsilon square, 1 over epsilon, etc.? Those things.
So they cancel out in the ratio again. So these are area counter terms. So when you take the ratio, you could imagine individually canceling them by putting an area counter term or a length counter term and so on. So these divergent again. So yeah, you can either individually cancel them in the sphere or the disk, or because they're local counter terms, they sort of cancel in that ratio that I was taking anyway.
But otherwise, you have a way of matching the epsilon that you use here to the epsilon that you used for the sphere.
Well, this was related to the subtlety that I mentioned, but let me not comment on that now. But basically, the idea is you suppress each thing by its eigenvalue, by just the eigenvalue. So you're using the same procedure in both. So you have some infinite product, and each term in the product gets suppressed by e to the minus epsilon squared times that particular eigenvalue.
Sorry, this is not too important. You must go on, but I suspect, if I'm right, if you did zeta function regularization, you wouldn't even see the 1 over epsilon square. These are all.
Yeah. If we did zeta functions, we wouldn't see them, but
I mean,
we were not very good with finding formulas in the literature for these zeta functions for the Robin boundary conditions. So we just did it numerically. We like these 1 over epsilon squared terms can be computed analytically because they just correspond to some UV stuff and they don't care about the boundary conditions. But I mean, there are probably analytic formulas for this 1.14858, which we just computed numerically. So anyway, yeah. Okay, so then we come to,
just to make sure, the total number of zero modes is 3 in the end, right?
For the sphere, it's 3. Yes. And for the disk, it's 2.
Okay, thank you. Yeah.
And I will show them explicitly now. Now we are precisely going to discuss these zero modes. Okay, so let's look at the sphere. So we had 3 zero modes on the sphere, the L equal to 1 modes. Those in this ratio are being written as chi1, chi2, chi3. PSL2C is a 6-dimensional group. So let's call its coordinates S1, S2, S3, which generate a SU2, and B1, B2, B3, which sort of generate the coset SL2C mod SU2, which is also hyperbolic 3 space. So that is one way of seeing that this is non-compact. And essentially the PSU2 volume is finite, so it will just stay in the denominator. And this chi and b is basically now a Faddeev-Popov determinant. So we have to compute this precise value of chi I to bi, this coordinate transformation. And for the disk, it's similar. So there are 2 zero modes, chi1 and chi2. These correspond to this tan theta over 2 e to the plus I5 functions. And the SL2R has 3 coordinates. There is a U1, which is preserved, and 2 which are broken.
Raghu,
So
sorry,
yes.
Sorry, I'm very stupid question. But if you showed us your disk saddle point, and that depended on theta, which was the angle of the disk, right? So then, since the saddle point depends on theta, even the U1.
Sorry. No, the U1 is phi. It's the azimuthal phi. That's the U1.
Theta is the direction from the radius. What is theta?
Theta is the coordinate from the north pole to the equator.
I see.
So north pole is theta equal to 0, and equator is theta equal to 5.
And you're thinking of the disk as half of a sphere.
Yes.
I see.
Yeah,
so it's
wanted to.
Yeah. Now I understand. It's basically a distance from the center of the disk.
Yes.
Okay, now I understand. Okay,
it
that's
is like a radius. Yeah.
That's why you had only 2 zero modes. Had it depended on phi, there would have been 3 zero modes.
Yeah.
Okay. Yeah.
Exactly. Yeah.
So you mean theta, Shiraj?
No, it depends on theta. Had it depended also on phi,
it does depend on phi, I think.
It does not depend on phi.
No. The saddle point is here in equation 1.12, and it only depends on theta. So basically the z-axis rotations of the sphere are completely invisible to the saddle point.
But when you compute the zero mode, it was U1 charge plus minus 1, right?
Yeah. So those are the chi zero mode. So when you act with one of the broken generators.
Yeah.
Sorry.
No, I was telling you. Go on, please.
Yeah. So if you start with 1.12 and act with one of those 2 broken generators, you will generate a phi dependence.
You've turned on momentum in the phi direction, basically, to get that zero. It's not like a diffeomorphism.
Okay.
Yeah. Basically, what I have shown, one way of saying it is what I have shown in 1.12 is just one out of a family of saddle points.
Right.
And that family is a 2-parameter family, which is generated by acting with those 2 zero modes that depend on phi. Okay. All right. So basically, here are the C goes 0 modes. These are the conformal killing vector fields on the sphere. So let's just look at number 1 and number 4. So number 1 is IZ. So when we make a phase rotation of Z, we see that the metric 1.33 is just completely invariant. So this is the U1 isometry of the disk. It's also part of the SU2 isometries of the sphere. On the other hand, if you look at number 4, this is a real rescaling of Z. And then you see that the form of the metric will be changed from 1.33. So this number 4 is a form of a broken generator. It generates a new configuration of sigma given this configuration of sigma in 1.33. So B1, B2, B3 represent the broken generators on the sphere, and S1, S2, S3 form up the SU2. Anyway, I think at this point, there's some math you have to keep track of to get all the factors right. But essentially, you take care of this gauge fixing and you find some number. Let me maybe just highlight one point, which is how the Liouville field changes when you act with these 6 vector fields, right? So we just have to make an infinitesimal Z change, and the sigma field changes according to 1.37. So Z tilde is the new Z. You plug it in, you find something just infinitesimal. And here are, for example, on the sphere, you get 0, 0, and 0 for these three guys. These are the SU2 ones. And the three B's that I was calling change the value of sigma by these functions on the sphere. And you will notice that these are precisely the L equal to 1 spherical harmonics. Anyway, and there's a similar story for the disk. So all in all, you do all the math, you keep all the factors correct. It took us a long time to figure out all these factors. Here's the final solution. So sphere and disk, on shell action, one loop determinant, some order one constants from the gauge fixing factor. On shell action, one loop determinant, some order one terms from the gauge fixing factor. You take the ratio, you get this. Let me just highlight some features of this formula. There's this sine pi over b square, and there's this alpha to the 2 plus 2 over b square. So notice that the mu has canceled out. Alpha was related to the boundary cosmological constant. And this fact that there's a 1 over b square in the exponential is reflecting the fact that we are in some semi-classical limit where b is small.
I'm sorry, I've forgotten
Yes,
what alpha is. Although you
alpha was minus 1 over mu b.
Minus 1 over mu. Okay, thank you.
And we are working in the limit of small positive alpha.
Okay. Mm-hmm.
Right, so it's just a number that depends on b and mu b.
Mm-hmm. Mm-hmm.
Okay, but there is one final step before we can compare to the matrix, which is that we were just talking about Liouville. There's also the minimal model. And the minimal model also has a sphere over disk squared, which is just given by the S matrix element relating the identity to the identity in the 2, p minimal model. And there's also some function involving signs and so on. So that you have to also multiply. So, and there is an additional fact, which is that the BC ghost non-zero modes. So we took care of the C ghost zero modes by this gauge fixing factor. But the BC ghost determinant on the sphere and the disk are equal. I mean, it's the square root, so it cancels in the ratio. So you multiply this thing in, and this 1.44 is the final answer. Somehow we computed things numerically, but if somebody was more powerful with zeta functions, they would probably see this one coming out exactly. So it's very simple. It's just p times alpha to the p plus 2. Okay. Let me pause here for some questions.
Sorry, Raghu, at the beginning you talked about how you're going to cancel the volume of the gauge group in the denominator.
Yes. Yeah.
But in the actual calculation you did, you never worried about the gauge group volume, right? Or did I? Yeah.
No, we did this here. So the gauge group volume was here. So this is PSL2C, right? It has 6 coordinates, which I have called here S1, S2, S3, and B1, B2, B3.
Okay.
The S1, S2, S3 are just finite. They generate a finite group SU2, so it has finite volume. And the chi and the B sort of cancel.
Right. And that statement is some precise statement that the chi and the B.
Yeah, it's because by acting with the B, the fact that the chi was a zero mode was a reflection of the fact that you're acting with the B, right?
And what about the radius of the, when you act with on a vector to generate a group, to generate a space of vectors, it depends on what group you're acting with, but also how big that vector is.
Yeah, that it cancels out in the ratio of the sphere over
the sphere over the disk. Yeah.
Fine.
Okay, thank you.
So it's important that these chi's and b's are related in that way. It's that we had a saddle point, and by acting with the b part of the group, we generated the chi zero mode. So that is why it's like a Faddeev-Popov gauge fixing. I could have said that I'm going to fix my PSL2C gauge by just picking out one of the saddle points of that infinite family. That's an equivalent statement.
Okay, thank you.
Sorry, Raghu, can you
Yes.
show that final formula you asked us to ponder over for a minute again?
144.
144. Okay, I'm a little confused. I thought all the mu dependence would drop out, but I guess
Which it has, yeah.
which it has, but alpha is really 1 upon minus 1 upon mu b, is it?
Yes, yes. So part of the game to match it with the matrix would
Yeah.
be to identify what mu b is in the matrix.
Okay, okay, I see. All right.
The short answer is that the mu b is related to the energy of the eigenvalue. Because we compute the disk is some resolvent, and the resolvent has some energy argument. It's trace of E minus X or E minus the matrix.
Yes.
So mu b is related to that energy that goes in.
And with
Sorry,
that
Raghu.
identification,
Yes.
this will match. Okay. Thank you.
Raghu,
Yeah.
this 1.000, is that expected that constant should be 1?
No, we didn't expect even such a simple constant. I don't know. Yeah, there was no
why is it-
expectation for what this value was. But the point is, this will match to the matrix or the large P limit of the matrix. Okay, so as I said, we are computing the sphere and the disk. Shiraz already asked. The sphere is just computing the integral. So you compute the matrix integral. It has an L expansion. You pick the leading term. Conceptually, it's easy. In the matrix integral, you solve for the density of eigenvalues. The integral is just some expression in terms of the density of eigenvalues. You just plug it back in and compute. And to just show you some expressions.
Very sorry,
Yes.
Raghu. You said this, I think, but the matrix integral is exactly the double scaling limit as discussed in S cube. Is that right? Or...
Yeah. Okay, let me say a few words. So, sorry, I'm being too quick. Let me zoom out a bit. So there is a duality relating the string theory that we discussed and just a matrix integral. This matrix integral is an integral over Hermitian matrices. There is no time over L by L matrices with some potential. The potential is a polynomial whose degree depends on P. P was the integer. So the first non-trivial theory is the 2,3 theory, which is the pure gravity. And one can get the pure gravity point by taking a potential, which is m squared plus m to the fourth, and then adjusting the coefficients to go to the double scaling limit. The next one, the 2,5, would have a potential, which is m squared plus m to the fourth plus m to the sixth. And then again, one has to adjust the coefficients to get to the double scaling limit. And the Salz-Schenker-Stanford matrix integral is the P goes to infinity limit of that.
Okay. I see.
So there's a whole family of matrix integrals, and
Thank you. Okay, thank you.
And the way we do these integrals is, you first get rid of all the U's, the unitaries, just go to the eigenvalue basis. But further, there are subtleties associated to this double scaling limit. But anyway, let me just say for the sphere on the right-hand side here is that, well, on both of these pages. So first, you have to engineer a one-parameter family of potentials. And this is a one-parameter family for each P. This parameter is epsilon, which controls the double scaling limit. So you have to go to the epsilon goes to 0 limit at each P. And you have to adjust the coefficients of the potential so that its density of states near the cut endpoint looks like this. This is the cinch of Arc-Kosh formula that I showed earlier. P is 2m minus 1. So this is the definition of the model.
Okay.
Engineer a potential, one parameter family of potentials. So these are just single cut solutions. So the eigenvalues are supported on one cut. You zoom in near the left edge, and you're supposed to ask, what does the density of states looks like near that edge? And the cinch of Arc-Kosh formula was found in this paper of Seiberg, Stodecker, and Moore.
Sorry, Raghu.
Yes.
You're going to compare with the matrix, just a matrix integral, and there's a definite normalization to that matrix integral. Couldn't I
Again,
multiply the matrix by a p-dependent normalization and get any answer I want?
Again, the sphere over disk squared helps you get rid of that normalization, because the disk will be proportional to L, right? So the like here, so the sphere, the log of the sphere has an L squared in it. The disk quantities are all again proportional to L. So
sorry, what was L? I forgot.
L is the size of the matrix. So we are integrating over L by L matrices.
Okay.
So the free energy is proportional to L squared, but the density of states, the resolvents and stuff like that are proportional to L.
Sorry,
because
so
L is the number of eigenvalues.
Right. Your dictionary was that the matrix integral was the sphere partition function. And what is the disk partition function?
That is in equation 2.4. So the disk partition function is, 2.3 is trace log matrix minus X expectation value. And X is related to mu B. So the disk in the Liouville came with a mu B parameter. And the disk in the matrix integral comes with this X parameter. It's just this quantity. If you took a derivative with respect to X, this would be the resolvent.
Sorry, an expectation value means dividing by partition function? What?
Expectation value here just means doing the integral over H.
Without dividing by the partition function?
Yes, without dividing by the
I see. And then, so now suppose in the measure for the integral, there was an ambiguity. You say sphere by disk square, that ambiguity cancels? I can't see that.
Well, we will come to this. You're right. It doesn't cancel in this way, as I was saying. So notice here that what I'm calling sphere is really log of the matrix integral. Right, because it's the free energy.
Right.
So it's the log of the matrix integral is the free energy.
Okay.
But there will be some ambiguities. Like I was telling that in the Liouville side, there are these integer powers of mu. There are similar difficulties in the matrix integral, because if we worked with a vanilla matrix integral with L finite, the free energy would be some number. But because of this double scaling limit, you also have analyticity or non-analyticity in epsilon. This epsilon is the parameter controlling the double scaling approach to the double scaling point. So let's just look at a concrete example. So in 2.5, I have shown the free energy of the 2,3 model. So there are some even powers of epsilon and some constants. And then there appears an odd power of epsilon. So in the dictionary that I'm using here, the epsilon is like mu to the 1/2. So you see, this is mu square. And what you really want is the term which is non-analytic in mu. So even in the matrix, there is hidden this structure. So yeah.
Sorry, I forgot what epsilon was. What is this epsilon?
Epsilon, so for each P, you have some matrix integral. But there is the potential is arbitrary, right? The potential is a polynomial, but the coefficients of the polynomial are arbitrary. So you have to make a one parameter family of polynomials parameterized by this epsilon. In other words, it is L times epsilon to the some power is the string coupling constant. Right. So what happens in the double scaling limit? We take the size of the matrix to infinity, and we tune some coupling to a critical value so that the product is held fixed, or L times the thing to the some power is held fixed. So that is that epsilon. So the double scaling limit is L goes to infinity, epsilon goes to 0 with some combination held fixed.
Thank you.
Okay. Right. So just to flash some result again, even in this G quantity, the trace log quantity, there are some terms that are analytic. Now analytic both in mu and in mu B. And we have to discard them. And we have to keep the term, which is these kind of fractional powers of epsilon. And once you keep all of that, correct, and you compute, you turn the crank, you find this answer like 2.13. So you see that in the large P limit, this front factor drops out. You just get 1 times P times that same alpha to the P plus 2. And but okay, that's all. So that's all I wanted to say, and let's just discuss. I think I've said what I wanted to say.
Wait, sorry, just before we get to the main stuff, just about this ambiguity business. What I understood is that you're saying that you assume that if there's a normalization ambiguity, it's analytic in epsilon. And so the non-analyticities will be unaffected.
Yeah.
Okay.
Yeah. Exactly.
Before we move on to the discussion.
Yeah.
Sorry.
Yeah, go on.
I just wanted to thank you for a wonderful talk.
Yeah. Thanks.